that within a few moments it should be visible to all of you. So for today's lecture, I am going to start with a terminal. This terminal can be started from anywhere, not in a particular directory right now. Later on, we'll have to start in a particular directory wherever we have got with us the root files data. So right now we are going to work without any data. So it is possible for you to just start a terminal from anywhere. And so I have started a terminal and I am going to type some root commands inside it. So like 1D, 2D spectra also are of 5 types depending upon the maximum number of counts. Namely, they will be of the type C. Okay, I'll type it for you. Let me start by starting root. So root is started. The 5 types of histogram, just as you have TH1 for one-dimensional histograms, you have TH2 for two-dimensional histograms. And then TH2C will be of the type byte, which can hold counts going from minus 128 to plus 127. Similarly, you have TH2S, which will be having the short integer 16-bit going from minus 32768 up to plus 32767, similar to one-dimensional. Then you have the integer, which is 32-bit, and then you have floating point, and finally double. So these are the 5 types of two-dimensional spectra. Which is the one which you will be commonly using? That will be, just as in the case of one dimension, the most common one would be TH1I, which you will use in all of your nuclear physics work. Similarly, in all your two-dimensional work is mostly going to be S rather than I, because here once you have a two-dimensional spectrum, I mentioned to you when we were studying it in lamps also, that it spreads out quite a lot. So there are so many channels. So you don't want to exhaust the computer resources. And the counts will never be that much on a particular channel because the counts are spread over many channels. So therefore the short is usually good enough. So let us start by defining a spectrum of TH2S type, and the command is similar to what we have done earlier. So if it was a one-dimensional, what did we do is that now at this point we declared it. Let me call it by the name age, just as we had done for one dimension. Then inside the bracket, first thing to do is to put the name of the variable again, that is age itself. And after that you have to put a title, and the title can be anything. So I'm going to put something here, my 2D histogram is what I have put. Now if it was one-dimensional histogram, then we would have written the number of bins. So I'm going to choose now make it a 10 by 10. Actually 10 by 10 is very small. You might remember that in lamps when we studied the two-dimensional spectra, we were working with at least 256 by 256 or more likely 512 by 512. But this is just a demo, and I'm going to choose 10 as along both the axes. So there are going to be 10 bins. Then comes the x minimum, which I will take 0, and x maximum I'm going to take 100. This is just for simplicity. And similarly along y-axis again, let me take similarly 10 bins and start it in the range of 0 and end up in 100. As mentioned earlier, the x-axis in 1D histograms, and in this case x and y-axis in 2D histograms, both are real variables in the case of root. So that's why you see this dot in the ranges 0 dot, 100 dot, but number of bins, that's an integer. So 10 is without a dot, and the 0 and 100 they are with the dot. So if I issue this command, then I will be declaring a two-dimensional histogram. So I have done that, and he gives me the information which is given here. Now just as I did for 1D, let us just for the sake of an example, place some counts in various bins. So I will choose the first 4 bins. Now the way of addressing the bins will have two numbers, one along the bin number along the X as well as bin number along the Y. In 1D there was only one bin number because there was only one dimension. But now we have to put two. So if I say H dot, then set bin content, then this will give me the chance to set any number of counts I want at a particular bin. If I say 1 comma 1, that means along the x-axis it is bin number 1, and along the y-axis also it is bin number 1. So this is the first bin along both directions, and let me put some number of counts in it. Anything you can put. I am going to put 120. So when I do that, then the first bin in the corner 1 comma 1 has been set to 120. I will just make a shortcut by using the up arrow and put counts in some of the other bins. So 1 comma 2, I am going to put 80 counts. So this gives me 80 counts in the 1 comma 2. Then let me set up something in 2 comma 1, and just for example I am going to take 20, and then let's put one more at the previous command was wrong. I put 120, so I just redo it. I wanted 120, and it is at 20 I wanted actually at 2 comma 1. So this is 2 comma 1 and 20 counts. So I have set it. Then let me set something at 2 comma 2 also. At 2 comma 2, just as an example, I am going to put 150 counts. So these are there should have been 4 commands, but one was wrong and had to be repeated. So I have set up 4 bins. I have set up the contents for 4 bins. Just as we did for 1D, as soon as we want, we can plot it and make a graphical view of it, and that's going to be done with the command draw. So since while we are declaring H, if we didn't make it a pointer. If it was a pointer, then I would have to use H, and then I would have to put the arrow. But here H is not a pointer, it's a histogram itself, so dot operator is to be used, and then I have to say draw. So this is very similar to 1D. So I'm going to first draw it, then I will show you some options which we have at this point. So you will get the 2-dimensional plot. It will be a bit ugly looking in the beginning because that is the default for root. So this will produce what is called as a scatter plot. So the plot has been produced. It is a 2-dimensional. You remember the view of 2-dimensional histograms from your work with lamps. So you know generally what a 2-dimensional histogram looks like. But in lamps you would have seen that the filled bins were given colors, and the colors were indicative of the counts inside it. In root, when you start, by default, he produces what he calls as a scatter plot, and this is on his own. He puts some scattered points, which the density of the points actually indicates how many counts there are. So this is not useful. So that's why we don't have this option, say in lamps. We just directly go to only one option, namely colored diagrams. But here root is more general, so he has many options, and the default option is a scatter plot, which in nuclear physics you will find it is not useful. So we won't like to plot it this way. So how do we go about setting it in the way that we want with the colored one? So there is a short way of doing it. I am first showing you the long way. You must know both. So as usual, we have to click here, edit inside the canvas. So it opened a canvas. The name of the canvas is C1. He plotted the 2D histogram. He put the title which I had written, and that was my 2D histogram. Now we are going to click view and then editor. So as we had done for 1D also, you click the view editor, and by now you know that the editor views that object. So there are many objects in the histogram, and the last click of the mouse will change the object. I am interested to change the properties of something. So I am going to do that now. I do want to change something here in the canvas also. This is my canvas. But first let's try to click the inside the histogram. So this is a 2D histogram. I click it and now you see it shows here H. H is the name of the histogram because we had provided that when we set it up. And the type is TH2S. And when you have reached to this situation, you see that the properties by which he has plotted are shown over here. So he has shown, for example, the title, then the type of plot, two-dimensional, and now what we are going to do is we are going to play with these settings: arrow, box, colors, and text. The present situation is scat, which is shown here in dimmed condition because that's what it already is. It's a scatter plot. If you want a colored plot, then COL, this is colors. So you click COL and you can see now that the colors have appeared. Now it looks similar to what lamps would have done. You start seeing the colored boxes. These boxes are rather big because of our big grid size. So we have chosen the range along X and Y to be from 0 to 100. This you can see along the axes, and we have decided to have only 10 bins. So along both the axes. So you see these rather big boxes. For real data, these boxes are going to be very, very small. So that we will come to. Now he has got some other options which I will show you. The first thing is that there is something called palette. So if you click palette, then you will see on the right hand side he has marked out what the colors mean. So if you now look at the colors, you notice that in the left hand most bin, okay, for doing that I will prefer to I go back now to the properties of the 2D histogram by clicking inside the histogram. And apart from colors, let me also switch on text. So this is another option. This option is not available in lamps, and we don't need it. It is only demo. So we are going to use it only for the demo purpose. Real data, you cannot afford to do this text. When you do text, you actually see the number of counts inside the boxes. Now in real life, these boxes are going to be really very small. So there's not going to be any space for putting the counts visible on the box itself. So obviously lamps doesn't have it because lamps is not meant for this type of data. So this is the text option. Now you can compare it with the color codes. So see this leftmost bottommost box is having 120 counts, and you can see the color scale. I am putting my mouse over it so it matches with that. This is having 80 counts, so it comes to this color scale. Then 150 counts is having the yellow uppermost color scale, and 20 is having the lowermost color scale. So this gives you an idea of what a two-dimensional plot is, and along with the color scale. And as mentioned, the default is scatter plot. So if you want to put scat and take away the color option, then you go back to the default, which is the scatter plot. So let's see now how we can achieve the same kind of plots using the command line, because this way of doing it is obviously through the graphical user interface is cumbersome and takes more time. So suppose you wanted to do it here, then the option is that inside the draw you have to put the option which you want to mention within inverted commas. So if you want colors, then the option is COL. COL means colors. So if I draw it with colors, then this is what I get. And there is an option color Z, COLZ, which will then display. See, if you watch carefully on the right, you will see the indicator bar appearing and what color means what. That comes with COLZ. So I am doing it. You will see the bar. So you see now this legend, display legend of color map appears on the right hand side. So that option is COLZ. So this COL is the option that we will be using always. There are other options we won't be using because this is nuclear physics data and this is the only good option. But anyway, root has got many more options. I told you about the text option. So text option comes by putting here text. So if I put text, then you will see actually the count numbers 80, 150, 120, 120. You see the count numbers only now. And if you want to have more than one thing showing, then you can put two things also. You can put both text as well as colors, as well as the display of the legend by putting text COLZ. Then you get this option. Next, the last important option. Now, one more option we are going to show, and that is a 3D plot. Now, this 3D plot, you know that is not available in lamps. Soon you will see why we didn't bother to put it in lamps, because again, it is not useful once you get used to it. To start with, it looks good, interesting, and you hope that 3D plots are nice to see and can perhaps give you some information. But actually, after you get some experience, you will notice that 3D plots are not useful for nuclear physics data, because we need high resolution and you can't display the things nicely in 3D. But still, it's an option, so we are going to do it just to show you. So here you see that when I go to the histogram, so I have clicked inside the histogram, then now I have gone to the H2S, so I enlarge the screen for you. You see that I am in the histogram. So I didn't click here, I clicked it. Actually, I can click anywhere, but not here, for example. This is the canvas. But if I click anywhere in the spectrum, then I get the H2S, and then you see that there is a plot and then there is a 3D also. So you can click the 3D and then you are able to see the three-dimensional picture. This picture can be rotated, so now I am keeping my mouse inside. You can probably watch my mouse screen is showing a different symbol which is allowing me to rotate. So you see that how it is. So this is your corner box. It has got this many counts. The box on the right has got less counts. The box diagonally across is having the maximum count, and there's one box behind it which can be seen more clearly when you rotate it. So you can see here how many counts it has got. So if you want to see the counts in all the boxes, you can turn the figure around and you can turn it as much as you like, and you can go to the other side of it and have a look. So this is your three-dimensional plot. I said it's not useful because this, you see, this example has got only four boxes which are filled, and the display is easy to understand. When the display is more complicated, then the colored diagram is more useful. So the colored diagram is actually the same as if you were looking at it like this. See, when you look at it from above, okay, so you have lost everything because you are looking above, but the colors, they indicate the height of the boxes. So if you are having this view, where now in these four boxes, in the present situation you cannot see anything because you are seeing the top of the boxes, but here we are using colors in their place to indicate the height of the boxes. So that is what a map display is. So if you were to wanting to do it from the command line, then the command line option is called as Lego, Lego. We did it before for 1D, but now you see it for 2D spectra. So you get this histogram plot by putting this command from the command line also. So that was it about the different options for displaying the 2D histogram. Now, just as we did for 1D, I have to, for the sake of completeness, I have to tell you these commands which are obvious. Suppose you want to know the content of some bin. So we say, let me go back to a 2D plot here, then it will be a bit easier. Okay, right. So as you can see here, the counts are 120, 80, 150 and 20. Suppose I want to see that those values on my command line. So on my command line, the command will be get bin content. We had done this for 1D also, but now we require two symbols. So 1 will be my cornermost box. Bin number 1 both along X and Y. As you can see, the expected number is 120. So you see I got it, 120. And like that you can get the contents of any bin. Now the other command which I had demonstrated for 1D is that this is bin number, but if you want it to relate to the X value, see X is going from 0 to 100. The bins are, the first bin is from 0 to 10, the second bin is 10 to 20, then 20 to 30, and like that. So suppose if I want to know the bin number corresponding to some value, then you can use the find bin command. So what to do is you say h, then dot, then you say get x-axis. So we are talking about the x-axis now. Similarly, we can do for y-axis also. So h dot get axis. There is nothing in the bracket, and then you point it to finding the bin. So find bin, and you give the x value. For example, if I have a number like say 35, I want to know which bin it corresponds to. Okay, so 35, let's say 35.3, and it's a real variable with decimal. So I have put 35.3, so that is coming somewhere here. So 1, 2, 3, it should be in the fourth bin, and we can check whether it is so. So here he gives the answer, yes, it is along the fourth bin. So this is the command, and you can do the same thing for y-axis also, when you want to find out the bin number corresponding to the x or the y value. Next you need to know is the integral command. The integral command is going to add up the counts in all the boxes which you in a certain range. So what you have to do for h integral, h dot integral, this is the command, and what you have to put is the starting, that is x minimum. These are in box coordinates, not in the value of x, but the bin number. So suppose you say this is the x minimum, bin of x1, and then bin of x2, that means the x range where it will finish. I am putting 1 1, and then comes the y minimum and y maximum. I have put 1 for all of them. So what will I get? Then there is nothing to add. The answer should be 120, because I am talking about the total counts in the first box. So this should give me the answer 120. But if you take another example, let's say I do from 1 to 2 and then 1 to 2. So x is going from 1 to 2 and y is also going from 1 to 2. Then what this should do is should add up the counts in all these 4 boxes. So you can do it, and then you get the answer 370. You can check it. So 80 plus 150. So the good thing about root is that he has got the calculator also right here itself. So anything you want, you can do it here. Plus 20. So this is what I got, and it's supposed to come to 370. You see it comes to 370. So this was about the integral command. Next we should do, again these are all very basic things you have done in 1D. Here it is very much same. That is how to zoom this spectrum, or to change the values of the range along the x and y axis. So the command is similar to what it is in the case of 1D, but here we have to specify which axis we are trying to work on. So first I show the command line command, so you know that it was set axis range. This is the same command as we used to do for 1D, but now there is a difference, that we suppose let's say I want between 0, instead of 100 I want to go up to say 25. But along which axis? That's what he wants to know. So this command as specified now, that would be wrong. Okay, and by the way, these are the x values, not the bin number. So better to put it with the decimal. And now he wants to know which axis, so I am going to say x. So this is the command, and when I do it, you'll see that I need to update also. So I can just click inside for updation purpose. So I clicked it. So you can see that he was supposed to go to 25, but actually he has gone up to 30. So that is an internal choice that he will make to make the pictures according to whatever he can. So you could do it for the y-axis. Let's try. So if I make this y, and on this side let me put 50 for example, So an updation by clicking inside the screen. So you see the y-axis, but he didn't like 50, he went to 60. So he made this picture for me. But that is obviously shortcut. So I am going to display, there are three important shortcuts. So one shortcut is that you first place the mouse inside this thing, inside your picture, and then you use, now this you won't be able to see because I am showing the screen only. There is a scroll button in my mouse. So nowadays most my mice have got the scroll button. So you just scroll with the my mouse button. So mouse scroll, and it will zoom as well as unzoom. So if I am here, I can zoom it like this, and if I scroll downwards, so I am able to arbitrarily go wherever I want with the mouse scroll button. But then I want to reach a particular place. So if I do with the mouse, it is zooming, but it is not panning to the place which I want. So instead of that, what you can do is you can just mark, I have marked some area. As soon as I release my hand from the mouse, then this much portion will get zoomed. See, this is what it did. So this is similar to, in 1D we used to just do like this along one of the axis. So that also works. So you can zoom along one of the axis like this. But now for unzooming, there is a command. Of course, you go here and click right click and then click unzoom. So you can do it. But now that we have this mouse scroll button trick, which so whenever you want to go back quickly, you see, this is the easiest. You go back to the starting point, and when you want to zoom, you just take whichever part you want to zoom and you zoom it as required. When you want to unzoom, you use the mouse scroll button. Okay, so that's enough about how to make a simple plot and how to zoom it, how to get the counts, how to get the integrals. So let's quickly go now. Now actually I need some data so that I can illustrate. So later on we will see how we can get actual data into the program. But right now, as we did for 1D, I am going to put up some random numbers for a quick situation here. So let me now then close this canvas. We are going to have a new one soon. And now you can see my terminal window a little bit, make it bigger for you. And let's define this time another type of histogram, th2 but f. So th2, instead of what we did up to now was the short integer s, let's go to the floating point, because I am going to put random numbers, Gaussian random numbers, so they will be in floating point. So here I am choosing th2f, and instead of h1, instead of h, which we have already, let's say h2 for example. So h2, then as usual you put the name h2 again in the bracket, and then now you have to give it some title. So I am going to call it as Gauss spot. So this will be a two-dimensional Gaussian, unlike a one-dimensional Gaussian. So it will look like a Gauss spot. You have all seen this Gauss spot when we did it in lamps. So we are going to do the same thing now in root. Then he wants to know, so this th2 is your histogram floating point. So it needs first number of bins. So let me put 100 bins. Then he wants range. Now values will be negative also. It's a Gaussian. Center will be at 0. So let's select, say, let's say -5 with a decimal point, up to say +5 with a decimal point. Then repeat along the y-axis also. Again I am selecting 100 bins, going from -5 up to +5 with a decimal point, and this is my h2. So if I try to draw h2 now, it would be blank because we have not filled any data inside it. So I am going to first define a function. So there, just as you, now this function I am not explaining because you will not need it later. It's only for the sake of this filling up the histogram with random numbers that we are doing functions. So functions is another big topic in root, but it is not of interest for us doing analysis of nuclear physics data. So I won't be covering functions, but now this is a two-dimensional function, tf2, and then it needs a name, and I'm going to call it as capital G, and let's say gxy. So the name of the function is gxy, then I have to repeat it here, and then I have to give the description of the function, and finally I have to give the range. The range will be the same, -5 to +5, and along the y-axis also I take the same. You can take anything else, it's up to you. So I am taking -5 to +5 in both the directions to match with the histogram range, and here I have to put inside the inverted commas the function. So I can put any function I like. It could be straight line, parabola, anything. So I am going to put Gaussian, and I want to put Gaussian in both the directions. So Gaussian is exponential, then inside the exponential bracket there will be minus, then x squared. So x multiplied by x. So multiplication sign is star, and then x again. So x star x. This is then divided by the sigma, the square of the standard deviations. So let me put 0.5. This has to be also squared, so let me put it twice. So this is for my x-axis. Then I should put y-axis. So I multiply it by another exponential, which is going to be along the y-axis. So minus y star y, and let me choose a different width. There I have chosen 0.5, so let me choose 0.25, half of that. This is just an example. Okay, so I made my function. So if I did not make a mistake in typing, I am going to release this command, and it worked out. He says that he has made this function. Now I am going to generate random numbers according to this function and put it for filling up my histogram. So H2 will be filled with fill random. This is similar to what we did for 1D, but in 2 dimensions. Now the function to be put has to be a 2-dimensional function, not a 1-dimensional function, and that is gxy. And then comes the number of samples, how many data we want to put. So let us put at least 1 lakh. So I am going to put 1 lakh samples, and that's it. Now I should draw it. So H2 dot draw. Now you know that draw without any argument will produce a scatter plot which will look ugly. So let us put directly the colors. So this command will be what I need. So I'm just making space so that you can see the graphical window. You see now the color plot. So it looks familiar to you because similar colored spot you have seen when we did the lamps also. Now you can you can, if on your own, if you want, you can change these widths to some other values and then have a look. Whenever you want to try something else, first you should zero it out, because fill random means it doesn't remove the existing counts, it keeps it. So if you were to do another fill random, then you would get overlapping with this. So if you want to clear it first, then that command is H2 and then reset. So H2 dot reset. If I do this, then all the counts will disappear to 0. So I did it. I'm going to click inside and you see it's gone. So that is how you can reset it, and then next time you can make a plot with some other function or in whatever way you want. So let me just continue with the same thing. So I have filled it and then I have drawn it back again. Now you might like to, in this example, have a look at the 3D picture, because this one will it's nice to see the 3D picture. It's a Gaussian spot, so a 3D picture would look good. So let's try that. H2 dot draw, but not in colors but in Lego. Lego is the bricks. So let's draw it with the Lego bricks and have a look. So this is what it will look like. This is your Gauss spot. You see how it is. It's a nice peak there. So this one is nice picture. You can turn it. So this is now view of the picture along the x-axis, and if you turn it here, then we are viewing from the side, so y-axis. So you see it's narrow because we put different widths. So it's wide this way, it's narrow this way. Then you can go to the back, but then it is symmetrical and like that. So this is the picture. The colored picture is similar to viewing it from the top. So if you were view this picture, if you view from the top, then it disappears because there are no colors. But then this is the picture of the so-called map display, color plot. You view it from above, and the height of the peaks is represented by colors. So now you have a clear picture what is meant by a two-dimensional spectrum. You have x and y axes, and then on the third axis you have got the counts. Now for the next topic, I want to demonstrate. It's called as a graphical cut. In the case of lamps, we had called it as a banana cut. Here it's the same thing, but it's going to be called as a graphical cut. So I'm going to demonstrate what it looks like on this diagram itself. So first let's go. You can see that if you want to make, for example, a graphical cut, then you can't do it, on this three-dimensional plot. It has to be first two-dimensional plot. So let me go back to the normal two-dimensional plot, and now I want to draw a gate, that is a banana gate, around this to select a part of it. So I am trying to explain how this banana gate is to be drawn. You will see more examples of it very soon in today's lecture itself. So the way to draw the gate is that you go to the view. You know about the editor. You can have that also if you want, but we don't need that immediately. But what you need is view and then toolbar. So in the toolbar, there are many tools, drawing tools given here. The last toolbar is shown with a scissors symbol, and if you hover your mouse over it, it says graphical cut. So this scissors tool is the graphical cut, and we are going to select it. Graphical cut, also called G cut or cut G in root, is the same as your banana gate or B gate in lamps. So we click that, and then you just click it anywhere, and then you move. Now in this case it's a bit different than lamps. You see that there's already a line he's trying to draw, but we haven't made the second click. I made only one click so far. You decide where you want to go, and at this point you put again a click. So I clicked it, you get a node there. Now he's trying to make the third one, so I go somewhere, clicked it, I go here, click it. But now when you want to close it, you click once more without moving the mouse, then it closes. So here many people go wrong. They are not sure how to close the mouse. If you go through the work being done by many people, they don't know, they are not sure how to close the mouse. They make a big mistake here. So closing the mouse, you are not supposed to bring the last point at exactly the close to the first point. You won't be able to do that because the screen resolution is limited. You must allow the program to close it. So that's why when you draw this cut, you have to allow the program to. I'll show it once more because it's important. So let's start by deleting this. How do we delete it? First of all, you have to select it. It's already selected, as you can see from my editor view, cut G. Type the type is T cut G, and the name of the variable is cut, all in capitals, cut G. I want to delete it, so see my mouse cursor is changing when I am near it. So I right click it, and then he has got some of the options we'll explore. One of them is delete. So I'm going to delete it. Before I delete it, I want to show you something important, that now that we have created this cut here, it's actually an object. The name of the object is cut G, and that is showing up in red in my editor bar. And in order for you to understand that, you go to your command window, And if you type now cut G, because that is the name of an object, is this object there or it is not there? If you want to know that, you just put the name of the object and press enter. It's supposed to give you the address of that object. So it says that it's there, this is the address. He knows it, it's existing. When I delete it, you will see that it will not be there anymore. So I do the right click and I do delete. When I try to do delete, it brings up one option box. In this option box, nothing is required, so just OK it. So OK it. So now cut, you see, is gone. It's no longer on the screen. So now that it has gone, if you try to ask for this cut G command from the from the command line window, you'll see that he is saying that it's not there. It's an undeclared identifier. There is no object like cut G because we deleted it. So whenever you are not sure about the presence or absence of an object, you can check it by typing the name of the object in the command line, and he will give you back the address. If he gives you an address, the number of the address, this is not important what the value is, but it exists. So now you know that it doesn't exist. So now I am going to draw the cut again. So when I draw the cut again, so to draw the cut, I choose the scissors tool. I'm going to just demonstrate the scissors tool. I have clicked it, and then see, I made 2 points. I'm making a third point. Now I want to close it. Okay. So some people, they think you go here and then try to click. That is wrong. Because if you do that, you can never really make an exact match, and you will end up with some thing which is not perfectly matched at the end. So what you do is, let's say you clicked here, but click twice. I'm going to click here twice, once, twice. Then automatically he will, it's not a double click, it's actually 2 single clicks at the same point. This is again a confusion, because in some places you will read that you should double click to close the polygon, but that is not double click. Double click is requiring 2 very fast clicks. That is not the case here. It is 2 clicks, one after another, to close the polygon. At this stage, my cut G has appeared again. If you try to check, see, of course you must spell it correctly. You see it's there. Now you can actually move it. As we saw in lamps also, we had facilities for manipulating the banana cut after it's created. Here there are some additional features, more than what lamps can do. For example, you can catch one of the points and then you can change the position of the node. So you can make the shape different even now after it's created. So this is just to demonstrate how it's done, and then you can move the whole thing. So this is, you can also add a new point also. He has even got that. Okay, so that's how you can do the cut. Creating the cut. Now you should know how can we save it, because we have created the cut, but as soon as we stop this root session, we will lose this cut. So maybe you are analyzing your data and this cut needs to be saved. So how do you save it? So there are 2 ways as usual. You can do it from the GUI or you can do it from the command line. If you want to do it from the GUI, then make sure that you are clicked inside this this one. So cut G is showing in the editor. Now you do a right click on this and click save as. So save as is there. Before we do that, I should tell you that we would like to change its name, because you see this cut G is a default name. It's not a meaningful name. So it is advised whenever you make a cut, change the name. Don't leave it as cut G, because then it will be confusing when we have more than one cut. So the first thing you do is change the name. So one of the options here when you right click is set name. So I'm going to click set name. When I click set name, then another window has opened up. He's asking what name you want. Presently the name is cut G. He's asking what name you want. So let me call it as my cut, just as an example. So I changed the name and then I said OK. Now if you were to, this screen has not changed, but if you were to click here, then you would see he is now calling it as my cut. The previous capital cut G is gone. If you were to check from command line, then he will tell you that cut G is not there anymore. But if you start saying my cut, then you find it is actually present. So you see how we were successful in changing the name. Now I'm going to save it. So I didn't want to save it with that default name, capital cut G. I wanted to save it with some better name. So that's why I went through this process. Now we are going to save it. So again, there are two ways. One is you go in with your mouse here, and then you click save as. That's one of the options here, save as. When you do save as, then it asks here, this is the window, it asks for the name of the file. So, and it asks one more option, but that second option we don't need. The first option only, you give it the name of the file, whatever file you want, you give it a name, and then you click OK, then it will happen. So instead of doing it, I'm going to do it also from the command line, so I'm avoiding doing it here. But if you want, you can do it, you can put some name here. So that's how you would have done it. And if you want to do from the command line, then I'll do it from here. So you will have to start with the cut itself. The name of the cut is my cut. So we start with my cut. Then it's a pointer type. So you will have to put an arrow, and then invoke the property of it, which is save as. So, and then inside the bracket, you will have to put the name of the file. So the name of the file, usually we will choose the same as the object itself. The object is called my cut, so we will like to make this also my cut, but dot and then capital C. This is now very important, this capital C. So capital C is often used for C++ code. So this is going to look like a C++ code. And next topic which we will be discussing are the C macros, and all macros should end with the capital C. And other C++ programs usually we will write with small C++, CPP. But macros we will put dot and capital C. This is just a convention, it is not essential. You are welcome to put any other name. It need not end in dot capital C. It's up to you, but this is the usual convention. That means dot capital C will be used for all macros of root. What is a macro? Well, I have not yet explained. It will come. So right now I am demonstrating how we can save it. So see, now I am going to save it. So I press enter. So it says that he has saved it. So actually, if you were to look at the directory, you will actually find that this file is now there. So since this is important, I'm going to just show you the presence of this file. So I'm going to just tab into one more terminal window, and then enlarge the font size for you, and do an ls command, and you will see that you should see it under my cut.c. Here it is. So this is the file which got created. You can even see what this file looks like by putting the gedit and having a look inside it. So this is the file. I am going to edit it and show you. So my editor has opened, and this is the content. So it starts with the curly bracket open always, and it ends with the curly bracket. Then it has the declaration of the object, and then the name of the object, and then afterwards all the nodal points, x and y coordinates of all the points are given here. So this is just like a C++ program. This is the way it has been saved, and this is going to be called as a macro. So this is your first example of a macro. Later on we'll see different types of macros. So this is a graphical cut saved as a macro. Okay, so I don't need this now. I go back to this place. So I was able to see. How do you get it back? So what I'm going to do is, let me delete it from here and then try to recover it from the file. So I right click and then I say delete. So again he asks option. I don't need any option, so I say okay. You see it got deleted. Now if I look here, my cut is now not there anymore. My cut, he says that it's not there. I want to retrieve it. So the way of retrieving a macro is the load command, dot and capital L. This means load. So I am going to load what am I going to load? So I know the name of the file. It is to be put without inverted commas. So load my cut dot capital C. When I do that, then you should see that it actually reappears in my graphical window. So I'm going to do that. See, it has reappeared. So I was able to delete it and then read it back from the file and get it back on my screen. And this is then the method by which you can save and retrieve a graphical cut. You also need to know how to use this graphical cut. That means suppose I want to apply the cut. So this is my data. I want to cut this data based upon the graphical cut. I want only that part of the data which is inside this polygon. I want to delete the part which is outside the polygon. How can I do that? So here it is. You go to the command line, then you say H2, and you know that H2 draw is what we do for getting it. And if you do H2 draw, it will give you the whole graph. It won't cut anything. If you want to cut it, then you put the command, of course within inverted commas, then square brackets are required, because then only the program knows that you are trying to make a cut using a graphical cut. And then you put the name of the cut, not the name of the file. The file has been saved, but that is besides the point. He is not interested now in the file. The file we have loaded back. The name of the cut, the name of the cut is my cut, not my cut dot capital C. That is the name of the file. The name of the cut is my cut, so my cut. This is what you have to put here. If I now complete it, then I will get my graph, but I will get the portion which is only inside the polygon. The part outside the polygon will be deleted. So I will show you, but in anticipation, by default the colors will disappear and it will go back to the that ugly scatter plot. But no matter, cut will be made. I'll show you. So here is the thing, the cut has been made. I lost the colors, but I could complete the cut. But I do want to keep the colors, so what do I do for that? Well, the thing is this, you can combine options. So previously you know that you have to put COL over here. So, but I am putting my cut. So where is the place for me to put color? So just put a blank and then put the second option, color. So this says you cut the data, but you please make it in color. I do that and then you see I have it. So this is how you can do the cutting of the data. And before I leave this screen, I want to demonstrate one small thing, and that is how to get the colors axis changed. So let me go back to the full one without the cut. So I am removing my cut option, asking for the full. See, I got back the full thing like this. Now I am interested that this, in fact, let me go for color with Z option, so that I am able to see on the right this also. I am able to see the color values. You will notice that these color values are on a linear scale. See that you see the numbers 200, 400, 600. The color changes. The gradation of the colors is on a linear scale. In lamps, the colors do not get graded on linear scale, always logarithmic, because we have found from our experience for actual data that, see, this is a very simple example. So these colors are looking all right on a linear scale. But when you work with real data, the logarithmic scale is the one which is more useful for the colors. That is the Z-axis. So to get that going over here, you click here and then you find that, you click in the canvas area, and then there is here, see, log scale X, Y and Z. So I want the Z axis, which is the counts axis. I want that to be in a logarithmic scale. So I click it and you see now you get now you see the color scale 10, 10 power 2, 10 power 3. And the appearance of the figure has changed quite a lot. So this is by default, lamps likes to display it this way. and doesn't have any option actually for linear, because we have found from our experience that these logarithmic displays of color are actually the most useful. So having said that, we will now pass on to a little more different topic, continuation of root only. So temporarily I am stopping now whatever I wanted to say about two-dimensional spectra. You've made some practice, you've done two-dimensional spectra, not enough, there's a little bit more to be done, but that will also come in the remaining part of the lecture. But first we have to know about getting root data into our process. See, this data we could generate by doing some random number generation, but this is not real data. I am interested in now to go to the next step where you are dealing with actual data in root format, and then you have to build up these graphs and all from the root files. So this next step is the first step in that. That requires a little bit of time, so it will be starting today, and then we will continue more about it later on. We will not come back to this elementary exposition of 2D displays, because this material is basically something which you can play back this today's video, and you can practice different commands. There is not much conceptually, it's more of the commands and graphical user interface which you have to get used to, so you can practice that. Now we go to slightly different concept, and that is to actually work with the data. For that purpose, I have made now in the website a new folder which contains root data for you, and I'm going to actually get this survey example which we did in lamps, then the telescope example, then the spot example, all the three examples which we did in lamps, and whose 1D and 2D spectra you already learned how to generate it in lamps and how to plot them in lamps. I'm going to do the same thing with root. So this is the plan. So first you must get the root data. So the original data was in the form of CSV files, which you know that lamps can read. But now I want root files, because root cannot work with arbitrary file types. He wants to work with root files only. So how can we do that? This I am not going to explain today. It will come in another lecture. Lamps is the program which can convert any format to any other format. So whether you have CSV, or whether you have ZLS, or whether you have .001, these are the three well-known forms. CSV is Excel sheet, comma separated values. Then ZLS is the lamps native format, and .001 is the IUAC native format, and root is for root only. So lamps can interconvert from any of these formats to any other format. So what I have done is I have already converted the files, because today's lesson I will not be explaining how to it will take us away from our main topic of today if I have to explain to you how to convert the files. So we will postpone that. But right now I need that. I need the data. So I'm going to try and get that data for you. I'm going to close this work from here. So I'm closing everything, and I will go to our website and show you from where you have to download the example. So I have opened the web. I am opening the website, and in the website go to the lectures tab as usual, and there you will find a new root demo 1. Up to now you have seen 5 lamps demos. Now there is a root demo 1, and the file to be downloaded is called rootstuff1.tgz. It works in the same way. We have to download it, get it into our download directory, then move it into our home directory, and then unpack it, and afterwards we'll work within that directory. So all you have to do is to click this and get it into your downloads directory, which I have already done. So I'll show you what my download directory looks like. I close this browser and I go to my downloads. I have to go to my download directory. So in my download directory I already downloaded it. When you do it, you will get this file. It's called rootstuff1.tgz. Now you have to copy this. So I right click and say copy. Then I go to my home directory, and just as I did with previous data, I similarly paste it here. So I got this root stuff1.tgz. I got it in my home directory. Now you right click and then do extract all. Extract here. So I'm going to click extract here. And when I do that, then root stuff1, it comes up as a new folder. And when I open that folder, these are the files which are contained in it, which I want you to have. So here there are three root files, and there are two macros. The two macros we will come to later on. The macros are showing with the C++ symbol, and they are ending with dot and capital C, whereas data files spot2.root, survey.root, and telis100.root are the examples of root data which actually I have converted. So the CSV files have been already shown to you earlier when we were doing lamps. Now using lamps, I have actually converted these same files into root files. And now we are going to use root to look at these files. So I'm going to demonstrate. Windows will come above this. So from here we are going to start root. Now what I'm going to show you first is called as a T browser. I should tell you that there are many ways of doing things in root, and this T browser is one of the ways in which when you first receive a root file, let's say you got some data, somebody has given this data to you because of the experiment which you did, so you have the file with you. Now it's possible that you don't know much about the file. It is a root file, that's all you know. You know the name of the file, you also know that it ends in .root, but you don't know anything else. You don't have no idea what is there inside it. So you would like to know what is there inside it, and then only you can get started with the analysis. But at this moment, we know only the name of the file, nothing else. So at that stage, you have to browse through the data. You have to go through it and browse it and to try to investigate what is really inside this file. And for that, again, there are two ways. So I am going to explain the first method. Is called as a T browser. You need to be familiar with both, but later on when you have gained experience, you probably will like the second method better because it's easier. But you need to know both, at least sometimes it's useful. So what are we talking about? We are saying that there is a file and we know only the name, but we don't know anything much about its contents. So the command in root is rather easy. It just says new and T browser. Now what is this T browser? It's actually a tree browser. You see, root data are arranged in what is called as a tree. So although the name has been given as root, but basically it's a tree. So there is a tree, and from the tree there are branches, and from the branches there are leaves. This is the way that the concept of root is. So you will need to be concerned only with the tree and the leaves. The leaves are the parameters which we are going to. There are usually you will not encounter branches. This thing is more general, so that you start with the tree and then you branch it into branches, and then from the branches you go to the leaves. So most of the time we will be dealing only with the leaves directly. So imagine that you have a tree and then you have the leaves. Don't worry about the branches that you will encounter only sometimes. Usually you will not encounter. So I'm going to say new and T browser. When I do that, then it gives a window which is like this, and this is called as the root object browser. This is similar to, you can say, like, displaying like a file manager, you can say. So from wherever I open, then he is showing all the directories which I have on my computer. He's showing all that, and so these are all other directories which I have on my computer. But right now we are inside root stuff one, so that he has highlighted. So this is, and under that these are the files which I have. And he knows about some of the files. Like if he sees that capital C, then he understands it is C++ code. So he puts the symbol next to it. And if it's a root file, because this is where he specializes, then this is your tree symbol actually. This, this small icon with three dots in it, this symbolizes a tree. And so he says that, okay, so you are having inside this directory spot2.root, then survey.root, and telescope teles100.root. Now I know this is a bit small, but unfortunately, even if I enlarge the window, the font is going to remain small. So I hope that's not a big problem for you. But when you do it, you will see it more clearly. So for now, let me pick up one of the files which I want to understand. So as a first example, yeah, for the T browser, I am going to choose the telescope example. So that is the last one in my list. So I'm going to click that. So when I click it, actually double click it, then he shows that it has got a lamps tree inside it. See, before I did it, it was looking like this. Now when I opened it by double clicking it, then he says that, okay, so this file has got a tree inside it. Actually, a file can have many trees inside it, but we will be dealing with files which always have one tree only. And then this is the name of the tree. It is called lamps tree. Why it is lamps tree? Because I actually use lamps to do the conversion. So lamps gave it this name. When you do with the real data, the name may be different. It won't be lamps tree. The name of the tree will be something else. But here the original data was CSV file, and then I did the conversion, and the conversion was done using a lamps program. So lamps gave it this name. But anyway, the name is not so very important. So if I now were to double click the tree itself, then he shows the leaves inside it. You see, so there are no branches from the tree, there are leaves. You can see the leaf symbol pictures. So he says, okay, so you start with the file teles100.root, then it has got a tree inside, lamps tree. Then there is a semicolon 1, because this is there is also version. Later on, when we try to make some changes, he may make a second tree also with the same name. This situation I am not describing, so ignore the semicolon 1, just think that there is a lamps tree, and there are two leaves inside it. The first is delta E and the second is E dash. So now you know, because we did it in lamps, so you know that this is what, yeah, so he is in the right track. Now we can actually double click one of these leaves. So delta E I am going to double click, and when you do that, you immediately see the spectrum of delta E on the screen. So this is what it looks like. Then he says, okay, let me try another leaf. So I click E dash, and it looks like this. So these are similar to the pictures you have seen already. This was that alpha source, this peak, and this was your Maxwellian distribution of the energy. So you have seen this picture, you know what it is. So in the beginning, when you start with root and you see these pictures coming just by clicking the leaves, you get the impression that root is then very easy. You just go to your data, open it in T browser, just double click the leaves, and the analysis is over. This is the kind of impression that you get at first sight. But unfortunately, no, because the problem is that you will notice that these are very poor quality graphs. Look at the step size, the bin size is quite big. So, and you also get the impression that root must be very fast, because see, of course lamps also appear to be fast, but this was small data. If you had bigger data, then you would see that lamps would be taking some time before the spectrum is built. This fellow seems to be very fast. Just we click and the picture is generated on the screen. But again, that's not the case for real data. Here he has produced a very coarse grained spectrum, and we cannot get a better result from this. This is only meant for quick assessment of your data. You are having a data, you want to understand something about it, and the purpose of the T browser is only that, not for the detailed analysis. So detailed analysis will not be done by T browser. It's only for your first look inside the data and to get a feeling about your data, and it is only for that purpose. Can we do two-dimensional plot? So this was one-dimensional plot. We learned how to do delta E by double clicking this leaf and the E dash by clicking this leaf. Can we get a two-dimensional plot, delta E versus E dash? Yes, you can. Again, it will be very crude one, but it is possible. So how do we do that? So in this case, you have to put your mouse over the lamp's tree. Then you have to right click, and from the right click, you have to choose Start Viewer. So this is one of the options, Start Viewer. You have to click it, and then a new viewer opens. So now this window I don't need for a moment, but I still keep it. So I have this window, and let me go to this viewer window. Preferably I will make this smaller. If you don't mind, I will keep it like this, and I keep the tree viewer here. Now you have to watch this tree viewer window. Unfortunately, I cannot increase the size of the alphabets here, so the font cannot be increased. Let me keep it where you may find it easier to watch. So this is called as the tree viewer. So the previous one was the root object browser, and root object browser also had a histogram displayer on the right, but now that was not useful for generating the two-dimensional plots. So two-dimensional plots के लिए we started the tree viewer, and that we got by right clicking the lamp's tree. Now here you will notice that he has got a list X, Y, Z. All three are empty. He has also got more, but they are not relevant. But he has also got delta E and E dash at the end, showing up as leaves. If you were to click one of them, it would appear in the previous screen. So you see, I'll just keep it side by side. So I double click this, it changes. So I can get back in my root object browser whatever I am clicking here. So this tree viewer is a kind of selector. It is asking what you want, and then he is displaying it back in the previous screen. But I am interested in two-dimensional plot. For that, there is at the beginning X, which is empty, and then the Y, which is empty. So I need to put these leaves. I want to put it over there. That is what I have to do. So I need to right click the X. I need to put delta E and drag it into the empty position like this. So this I will demonstrate again, because this method of dragging and putting is a bit difficult. So I am now see, actually I wanted delta E to come along Y axis. Not along X. It has gone along X. So let me push it. Let me put E dash over there along X. So I have to catch hold of E dash, then I have to bring it near the X, but then I must move it around until that X, which is now in blue, is changing to a different color, and then I drop it. Then you can see that I have successfully made X as E dash. The Y is still empty. There I want DE. So I catch hold of DE leaf and bring it here. If I leave my hand now, it won't work. You see, I have to make sure that I am very close to the correct place, and the color of that Y, it must change from blue to black, and at that stage only I must leave it. So this takes some practice, so you can try, and then I get the E dash and delta E along X and Y. Then I need to put an option, but I'll come to that later. So let me now go ahead. So you understand what I have done. I have made X as E dash, and I have made Y as delta E, and I did it by dragging the leaf into that position. Having done that, now at the bottom here, if you can watch my mouse, next to the spider, on left of the spider, there is a thing called draw current selection. It is in purple color, and the meaning of it is draw current selection. That comes if I hover the mouse. Under the mouse you can see draw current selection. I have to click that. So when I click it, then you can see that I have got the delta E plot, which is familiar to you because you have seen it earlier in lamps, and this is exactly that plot. But only problem is, where are the colors? This is okay, but I can see my separate lines for proton, neutron, triton, and the alpha, but the colors are not there. The colors to get is to be put in the option box here in tree viewer. If you see my mouse, I am here inside the option, and there I am going to put COL, or I can put COLZ if I want to see the colored band also. So let me put only COL, that should be enough, and then I have to hit enter. No, sorry, I have to click this draw current selection again. After putting the COL option here, I have to again click this view current, and now you see it. But unfortunately, the you can see the quality of the plot is very poor. The size of the boxes, that is the resolution of these colored things, is quite big. So I can't separate the proton, neutron, triton, and this is what. But this is meant for a quick view, so that is why this situation is there. You can't so you can't do much more, but at least you got some of your work done. And it is interesting that at this stage itself I will show you the scissors tool, and you can even draw the banana gate here, although we'll be doing it again later in a better way. Here we don't have enough resolution to separate things, but the process is the same as in any case. Also, one more point, you might think that why don't we here itself, if you say that this is not a good plot, why don't we try the binning here, because I had explained to you earlier that binning can be changed. So you might think that let's try it here. So you click here view and then editor, so you get the editor here, and then you go to clicking inside the spectrum. So he's showing the spectrum here, and then apart from files, pad editor, style, there is binning. So you click binning, and then you see he is showing the number of bins along the x-axis is 42, number of bins along the y-axis is 41. That's very small. We want to have 256 or 512 bins, but then he has got a slider here, and maybe we can change this also. So we can try, but you will see that is not possible. So as I slide the bin, he goes to worse, not better. This 42 is his best. We cannot improve it. If we try to type more here, he will not accept it. So it is 42. I type 256, let's say, and press enter. He doesn't like it. He makes a sound and he refuses, and he stays at 42. So we can't improve the binning from here. He doesn't intend that you can get higher quality plots. This was only for a quick look, so we can't do it here. Now let's see whether we can, in any case, can we draw a banana gate? I know that the resolution is not good to separate the three particles, proton, neutron, triton, but alpha at least is separable. Is it possible? Well, yes, actually it is. So if you do view and then you say view toolbar, and you find the scissors tool here also, and it works in the usual way. You can definitely click it. Last point, you click once and then you click a second time. So you can draw the banana gate. Not that it is going to help here. We'll do it in a better way soon. So a few options which I have not explained are that when drawing this, you can also do a smooth line in the banana. This is one of the options Root has got. We don't have it in lamps, for example. We have only the simple line option. So if at all ever useful, then one can use it. I don't really see much use for it, but if somebody wants, he can use it. Okay, so that was it about T browser. So my comment about T browser to you is that this is something that you can learn. It's not many steps. You will have this video. You can try it out and have it with you and practice it. But its purpose is not the final analysis. It cannot do it. So if anybody thinks that this is all there is to Root, you open the Root file with your T browser, double click the leaves, or make 2Ds out of by dragging the leaves, and everything is completed. Unfortunately, no. This gives you only low quality plots, which is meant for quick look at the data, not for actual work with the data. So let's see what other way is there, and later on when you learn the other way, then you will see that this Root browser is actually not required at all. You can even avoid learning it if you don't want to learn how this tree viewer worked for you. So let me close the whole thing out, and let's start it in a different way. So I'm starting root again in the same directory, and for now let me do the simple example of that survey.root. So that was, some survey which we did with age, height, and weight of persons, and it was a small file with limited data. It was given for demonstration purposes. So now we learn how to open that file from here. Instead of doing a T browser, you say TF. Now TF is going to be your file. It's going to be a T file, and you can. It's commands are similar. New T file, and then you give it a name. The name is, in this case, survey.root. So this file should be existing in the directory, which in this case it is, and this is the way that you can open a file with this command. So I'm not doing T browser, I'm opening the file itself by using new T file. The left side TF, this can be anything. This is a variable of your choice. I called it TF, and the file name is survey.root, and I open it. And when I open it, he says yes, he was successful in opening it because he has given a pointer to it. So it means that this file was found, and now TF is a valid object. So what we do at this stage is, for diagnosis purpose, we learn the following commands. This is more important than learning the T browser, so you should learn this for sure. So the first command is .ls. You may know ls command in Linux, that is for listing of files, but this is not that. This is for listing the details of survey.root which you have opened, and there's also a dot in front. It is not ls, but it is .ls. When you execute the .ls command, he gives you some information, and that information, the vital information, is the name of the tree, and he tells you that the name of the tree is lamps tree. You can see that here. So this is how you will discover the name of the tree, whereas previously by using tree browser we also learned how to discover the name of the tree which is inside the file. But this also gives, so this is going to be easier than using the T browser. Now we know the name of the tree, and we would like to get some more information that, okay, what are the leaves of the tree? Because we need to know the tree and we need to know the leaves. Then we can proceed. So in order to know what are the leaves, first we need to know the tree. That we got, lamps tree. So you say lamps tree, and then ask him to tell what are the leaves. To print out the leaf names, we give an arrow and then ask him to print it. This is the command, print without any arguments the tree. This gives an information about the tree. So this print command is print information about the tree, and when you do that, this is what you get. So he says, all right, the first part is that there are 20, and you see there were only 20 events in this file. You might recall when we did this example in lamps that we made a CSV file with 20 lines. So there were only 20 lines in the file, and so first comes the name of the tree itself, which you already know. It's called lamps tree. Then he tells you the size of the file in bytes, which is okay. And he tells you that the tree compression factor is 1 because there is no compression here, which he could do. So that's okay, not important. But now in the next things you see marked as BR. BR means branch. Actually they are leaves for us. So the first one is age, then is height, and then is weight. You see 0, 1, 2. So BR0 is age, and BR1 is the height, and BR2 is the weight. So we have got 20 people, and the age of the 20 people is in the first leaf, that is 0. Next one is the height, and the next one is the weight. And he also gives you the type. So age stroke s, this means that it is of the type short integer. So this is also important to know what type it is. So the type is given in the after the stroke. So the name of it is age, that you can see from here, but its type is short s. So this is also of interest. And now we know the names of the leaves. This is all that we need to know. We know the name of the file, we know the name of the tree, and we know the name of the leaves. Having got this much information, now it becomes very easy. First you give the name of the tree. Name of the tree we know. The file we already know because we have already opened it. So t file command was already given. So this file is at this moment open. Now we need to give it the name of the tree. So we know the name of the tree. And then we would like to draw it. Then we will get a picture of it. So we say draw. Now we have to tell what we want to draw, and we have to give the name of one of the leaves over here. So let's draw the leaf edge, for example. And I need now space for the window to come. Graphical window will appear with the edge displayed as a one-dimensional histogram. Yeah, okay. So I did it, and this is the edge distribution. So this is, you will see that this is better than your T browser. Okay, later on we'll make more progress gradually. But for this example, we don't need much binning, so this picture is good enough for this example. If you were interested to bin it, then what would you do? You would have said view and then editor, and then gone into the histogram, and then you would have asked for binning. And when you tried the binning, then now he shows that there are 64 bins. For this example, 64 bins is quite a lot. We don't have to have. And now he shows in the slider that you can have more bins also. So see, I am able to get even 256 bins if I want. And if I want less, then I can go down to even 50 bins. So here he has got the chance for you to do some rebinning, which is more meaningful. But not all the options which you need. But still, for this simple example, it's good enough. So you can do this for another tree, another one. So let's say height. So now I get the spectrum of height. You see, these ones you have already plotted before in lamps. They are similar, though not exact. If you run the lamps example again, you will see, because the bin sizes are a bit different, so the pictures don't look absolutely the same, but they are similar. Then you can do for weight also. So I did it for weight, and I got the one-dimensional spectra which lamps was also doing. And what about two-dimensional? So now for two-dimensional, you take the tree and then you draw, and then you put x-axis and y-axis. So if you want to know, let's say, age versus weight, then you can take this way, or height versus, I would like to put weight and then age on this side. Okay. We also want to do with the height. So let's start with height versus the age. So this is height versus age. It did not draw properly because of the options. So this is the what we want to draw. Then there is one more option here. This is called gate, and we don't have any gating, so you have to put 0. And then we have to put the option. In this case, it is color plot. So this is what I need, and then I get it. One issue is that the color is in yellow, which you can hardly see, but it is there. If you would like to change to a brighter color, then in this command I will not explain right now, but just for giving the picture a better feeling, I will type it in. It is called a set palette. You don't have to learn this command now. Set palette, instead of palette default, I go to palette 1, so some color change will be there, and then I draw it, and now I have some colors which I think are better, more easily seen on my screen. So in this way, so here when I was doing this explaining lamps, I wanted to show you the correlation, and I made the point that you see the height, which is along the y-axis, is correlated with the age along the y-axis provided the age is below 17 years of age. But by that age, the people peak in their height, and then afterwards, then there are no more. Then you get a saturation. Of course, there's one person here whose height is very small, despite of being an adult of 45 years of age, and okay, so he's a short person. But otherwise, so correlation in the beginning, and then afterwards it saturates. So this was height versus age. You can do weight versus age, and so on. So this is weight versus age. Again, you see the weight. The baby is growing up, so the weight is increasing. But afterwards, then here, after you are an adult, then your weight is not related to your age anymore. Okay, so that was some explanation. You might be interested to see the 3D views, but actually also they don't look that great, so I am not doing it. You can try to do it and see the 3D views. And I will now ask you to compare these pictures with lamps. This you do on your own. So I'm going to do only one point more, and then we stop, because I think at 4 o'clock we have to give up this link to another lecture. So for last thing is to show you what we mean by this second parameter. So I am showing you this 0 here. This is actually a condition. So you can put a condition here. So this is called gating. So I want to make the same picture, but I can put some condition here, and the condition is to be put within inverted commas. And I say, for example, this is just say, plot this, but only if the weight is more than 30 kilos. So all the children, babies will be left out. So these 2 points here, they will disappear. Rest of the points should remain. So let's have a look. So you see it has changed. Actually, the axis also changed. He scaled the axis starting at 30. So he removed the points. You can make the condition more complicated. You can say weight greater than 30, and so this is the usual AND operator in C++, logical AND operator with a double AND. And I say that the age, so the weight is greater than 30. Okay, and the age, let me also put it something. Let's say the age is also is say greater than, let's say, 20. So I should get only this part. I should get only this part if I make this condition. Usually we like to put brackets here. I'm not sure whether they are going to be required in this case. But if you want to be absolutely sure, then it is usually useful to put the brackets here. You see, it got rid of the some part. So with this we stop, because we have only 5 minutes left.